Hey everybody, this is Mr. Graybo. I'm going to go over the notes about seafloor spreading, and then when we're done with the notes, you can do learning target 6. So you should be able to do learning target 1, 2, and 6 after you watch this video. So we've done the continental drift notes. This is learning target 1, and we've covered the layers of the earth. That is learning target 2. And then we're going to skip over convection and driving forces for now. We're going to do that a little bit later. We're going to jump into seafloor spreading. This is learning target number 6. Okay. So fill in the blanks here while I go through the notes. First thing I'd like you to do is think about what do you picture the ocean floor looking like. Most people would imagine something that looks like this. Not a whole lot there, just a pretty blank flat ocean floor. But one thing, I'm just going to fast forward past this video here. One thing that we noticed, and that scientists noticed during World War II, when they used this new technology called sonar, is that, well, first they were looking for submarines under the ocean floor, or under the ocean, that's what they were trying to discover. But what they were noticing is that there was an underwater mountain range. And so they discovered this mountain range just poking up, not out of the water, but like down on the ocean floor. They could see this mountain range that went all the way up and down the Atlantic Ocean. And so after World War II, they went back and investigated and found out some pretty interesting stuff about that. And it helps to explain why, or how rather, continental drift happened. Remember, Alfred Wegener couldn't explain how the continents drifted apart. Well, this is the theory that explains how it could happen. So let's start here. What is the theory of seafloor spreading and where it started? So it was proposed by this guy named Harry Hess in the 1960s. He was also in the Navy in World War II, and he was one of these guys that discovered that mid-ocean mountain range called the Mid-Ocean Ridge. So the ocean floor is made of basaltic magma. So it's a rock called basalt. It's a heavier rock, heavier than the continents around it. And what happens is it rises up from the mantle, and that creates new ocean floor. So as that magma comes up, you see in the picture on the right-hand side of my screen, the magma comes up and it pushes the rock to the side. So as that new magma comes up, that old rock gets pushed to the sides, and the continents are going to move along with the ocean floor. So you see in the picture how the ocean floor separates and the continents are just kind of going along for the ride, kind of like when you put food on a conveyor belt at the store, the food goes along for the ride. Well, the ocean floor takes the continents for a ride and pushes them apart. So he thinks that this is where that's happening. This is the source of it. It's called the Mid-Ocean Ridge. So as you can see in the picture, first the picture up at the top, we see Pangaea splitting apart. We just didn't know how that happened. We knew that the continents were once connected, but what is driving them apart? And as you see in the picture in the bottom right-hand corner of my screen, you see underneath the water, there's this mountain range. That is where lava is coming up the ocean floor, and it's making a ridge or a small mountain range under the water. And that's where it's pushing apart. Okay, so what's the evidence of this seafloor spreading? So as scientists began to investigate the seafloor, there's 3 major pieces of evidence that were found that support this idea. Number 1 is the age of the rock on the seafloor. That's one thing that we investigated yesterday. Number 2, the sediment thickness across the ocean floor. That's another thing that we looked at with the washers. And then a third one I'm going to briefly touch on. It's called magnetic reversals. There's a pattern with the magnetic reversals on the ocean floor as well. Okay, so the first bit of evidence, this should look kind of familiar to you. We looked at this a little bit earlier in the unit. But as you see in the middle of the ocean, right in the middle of the Atlantic Ocean, you see all this red, and then it's yellow, and then green, and then it turns blue. So the youngest rock is right in the middle, and it gets older and older and older as you go to each side. So it makes a symmetrical pattern on each side. And that's what we were trying to model yesterday. The youngest rock is in the middle, and it gets older and older as you go to the left and to the right. So that's what they noticed on the seafloors. The age of the rock has a symmetrical pattern in the ocean. Okay, so as new oceanic crust forms along the mid-ocean ridge, the older oceanic crust is pushed away from the ridge. And that would explain that pattern, that symmetrical pattern that we're seeing. Okay, so prediction, if the mid-ocean ridge makes new crust, is the Earth just getting bigger and bigger? Okay, so that new crust that causes the continents to move farther apart, the Earth doesn't get bigger because the older crust is also being recycled and pushed underneath continental crust. So as you can see in the picture, in the middle, we have our mid-ocean ridge, and it's pushing the ocean floor apart. Well, if it's pushing apart there, where the edge of the plate is on the other side, it's got to be colliding with something. So if it collides with a continental crust, it's going to go underneath it because ocean floor is made of basalt and it's a heavier rock than the continent. So it's always going to sink underneath. We call that subduction, where it sinks underneath a continent. So the Earth doesn't really get bigger. It gets bigger in the oceans, but then it gets smaller on the other side of the plate. Okay. So thinking back to the last lesson on forces, let's see, we didn't cover this yet, so we're going to just skip over that. Okay, so here's our plate boundaries. And we can see the direction of the plates. So if we have plates moving one direction on one side, they're going to be pushing the other way on the other side. So if it's separating on one side of it, it's going to be sinking on the other side. All right, evidence 2 is the thickness of the ocean floor sediments. Okay, so as sediment gets deposited on the ocean floor, this buildup of sand on the ocean floor, things dying, things like fish dying, little shelled animals, all that sinks to the bottom of the ocean floor, and that sediment builds up over time, and it creates sand on the bottom of the ocean floor. Well, if we look at the pattern, we can see there's a pattern with the thickness. And we tried to model that yesterday with the washers. We noticed a symmetrical pattern, again, with the washers. So what happens is we get the sediment is thicker away from the ridge. So if you think about it, the longer the rock is there and exposed, the longer it has to collect more sediments. Because older rock is further from the ridge, that's got the most sediment. So new rock at the center is going to have the smallest amount of sediment. So it creates that symmetrical pattern, and you should have seen that yesterday with your washers. The thinnest sediment was in the middle, and then it got thicker and thicker and thicker the older the rock is, because the oldest rock will collect more sediment over time. So again, that symmetrical pattern is proof that it's separating and it's pulling apart at that ridge. Okay. Third piece of evidence is the magnetic reversals. So we're not going to go too far into detail with the magnetic reversals. We just need to know that that is a piece of evidence. Magnetic reversals are when because the Earth is like a magnet, we have a North Pole and we have a South Pole. Every once in a while, every few thousand years, that pole switches. The North Pole becomes the South Pole. It's like the magnet reverses. Okay? And when magma cools, it can record those little pieces of iron point a certain way, either towards the North Pole or towards the South Pole. And when that magma gets collected, it records which direction the pole is. So the Earth has got a magnetic field, and the volcanic rocks on the ocean floor have iron in them, and they're magnetic. So what they do is the magnetic minerals in the cooling lava on both sides of the ocean floor, they record which direction the North and South Pole is. By looking at the little pieces of iron inside the rock, we can see which way the North Pole was during the time of that formation. And again, it forms a symmetrical pattern. So it's just one more piece of evidence showing the symmetry around that mid-ocean ridge to prove that it's separating. Okay, so if we look at how this happens here, here's the mid-ocean ridge. As that lava cools, it lines up a certain direction. Whichever way the North Pole is, those minerals are going to be pointing that direction. So every few thousand years it switches, and you can see it in the rocks. So you can tell which direction it was during that time. But what we see again is a symmetrical pattern. Okay. All right, so I think that should be it. We've covered the 3 pieces of evidence. Let's see, we'll come back and do this stuff. We'll do this later. The stuff about what's going on underneath the plates. We'll talk about that later. So what I'd like you to do with the rest of your time today is I'd like you to go into your green study guide, and I'd like you to work on learning targets 1, 2, and 6. Okay, so you should be able to do 1, 2, and 6, and then we'll touch base tomorrow when I get back. All right, message me if you have any questions. Thanks.